All right, so we left off last class, we talked about cis-trans isomerism and FAC-MER isomerism. And so this example was practicing. Some of those people in the class have already had some time to do so. So if you're watching the recording, pause and give it a shot. And we'll get into it. So we've got chromium for our metal center for this first example, and we've got 3 aqua groups. I'm underlining the aqua groups in red because red for oxygen. And then we've got 3 chloro groups. And I think chlorine is usually green. We can represent it as green here anyway. And these, since they've got 6 ligands, are going to be octahedral geometry. So we're going to have something in the up position. We're going to have things off to the left coming forward, going back. I'm leaving off the hydrogens just for keeping things a little bit less busy visually. And we're going to have our 3 chloro groups. So we've got our up position oxygen, we've got our down position chlorine, we've got 2 chlorines to the right, we've got 2 oxygens to the left. So this would be one of our isomers. We also have another version of this that we can draw. We're still going to have chromium in the middle. I'm going to choose to have oxygen in the up position. We'll have oxygen in the back left position and in the down position. And then we're going to have our 3 chloro groups filling out the rest of the, what we would probably think of as square planar things in the XY plane. So these are the 2 possible isomers for this compound. Who knows what this left one is called? What would the prefix be for that isomer? Thinking about cis-trans or FAC-MER? It is one of the FAC-MER ones. Yes, the left one is FAC. So if we connect these 3 oxygens, this would make up one of the faces of this octahedral complex. Octahedral, the octa standing for 8, the hedra part meaning faces, so 8 faces. This makes up one of the faces. This is the same shape as a D8, an 8-sided die. And then this other isomer is the MER isomer, MER standing for meridian or meridional. So we've got these oxygens all lined up. These are all in the same 2-dimensional plane, and the CLs are all in their own 2-dimensional plane. We can think of them as like meridians or north-south lines on a globe, or east-west lines on a globe. So those are our FAC and our MER. And then we've got our second compound. We've got cobalt this time. So cobalt in the middle, we've got 2 amine groups. We've got a chloro group, and we've got an oxalato group. I think it's oxalato. Oxalate. Oxalate is toothy. It's bidentate. So it takes 2 of the 6 spots, and our other ligands each take 1. We've got ammonia. I'm going to put the amine groups, the nitrogens, over on the left for no particular reason. And we'll put a chloro group down and coming out to the front. This means that our oxalato group is going to have the up positions, and those 2 things are connected. We'll just draw in a solid line representing the rest of the oxalate, the 2 carbons that are in between those carboxylic acids. So that would be one of our isomers. There's another way that we can arrange these, and that would be swapping one of the nitrogens and one of the chlorines. So if we swap those two groups, that'll give us the other isomer. So cobalt in the middle, we're leaving our oxalate connected to the top and the back right positions. We've got a nitrogen coming back into the left, one coming out into the right. And we've got our chloro groups, one down, one coming out into the left. What type of isomers are these?
Cis and trans.
They are cis and trans. Which one's cis?
The one on the left.
The one on the left is cis. The nitrogens are both next to each other. The chloros are both next to each other. And what about the right one?
Trans.
This one would be trans because the nitro groups, the amine groups, are opposite each other. Are there any other isomers we can draw?
Do you get Cl and NCl? Or no?
I'm not sure exactly what you said, but the answer is yes. There's another one that we can draw. So if we flip the spots for the amines and the chloros, we can have a different trans configuration where our chloro groups are opposite each other. And that would be different. And then I think any other configuration that you can come up with would just be a rotation of one of those three configurations. So that's part of why I left the oxalate kind of locked into that spot, and then we just moved everything relative to that to help not get confused. Questions about the fun that we're having with isomers?
So is the oxalate just 2 oxygen then?
It's not just 2 oxygens. It's C2O4 2 minus. So there's 2 more oxygens that aren't shown. There's also the carbons that are connecting them.
Is that what it would look like though, or would it be drawn out completely?
I am going to guess that if somebody was drawing it by hand, they're going to draw it out this way. If you see it on like a figure in a question, it might be drawn out everything all the way.
Okay.
It might also just be shown this way for brevity's sake,
Okay.
to keep things from being confusing. Other questions? All right, we're having a good time. We also have optical isomers. So optical isomers are a special type of stereoisomer. Optical isomers are non-superimposable. They cannot be overlaid. Molecules that exhibit optical isomerism are chiral. In case you wanted to learn more words, don't worry, here's some more words. So chiral is a new word for us. These isomers are enantiomers. They're chiral isomers and exhibit optical activity. That optical activity is that they rotate light. Typically, this is going to happen for octahedral complexes, so where they've got 6 groups attached to them. You could also have it happen with tetrahedral complexes, but they have to all be different groups. You'd have to have 4 different ligands. So oftentimes when we're talking about optical isomers, we think of them as being right-handed and left-handed. Both of my hands, both of your hands, assuming that they're the typical kind of hands, you've got 5 fingers. Both of them have 5 fingers and a palm and thumbs, 4 fingers, whatever you want it, however you quantify it. And you can make them look like each other, but there's no way that you can rotate your hands and have the palms be on the same sides. They're mirror images of each other. And that's what these optical isomers do. So you can, however you want to rotate them, there's no way that you can rotate them where they overlap perfectly and they're the exact same thing. And if you look at them in a mirror, one is just the other one but flipped in some way. So those are optical isomers. Let's see if we can figure out whether the FAC or MER isomers of these compounds are optically active. So first thing we're going to need to do, of course, draw out the FAC and MER isomers. We did this already. A lot of this sort of stuff is typically easier if you have a model or multiple modeling kits and you can build them. Okay, so again, leaving out the hydrogens just to keep things a little bit cleaner. Wrong thing. All right, so we've got FAC and MER, the facial and meridional isomers. And to see if they're optically active, I'm drawing this dashed line to represent a mirror. So we're going to draw the mirror image of each of these. And I drew the wrong metal. That should be Cr. So anything that's in the up or down position stays in the up or down position, but we're just flipping the things that are on the right, putting them on the left. The things that are on the left, we're putting them on the right. So we draw our mirror images, and then we ask ourselves, can we get them to overlap? Can we rotate one to get the other? Just looking at our FAC and our MER. Not trying to get our facial ones to look like our meridional ones, because that's never going to happen. Is there a way that we can rotate this facial isomer to make it this other one? We would just rotate 180 degrees around the Z, that's the vertical axis. So if you just pick it up, spin it 180 degrees, it might work other ways too. Then these are the same. So they're not optically active. They are mirror images, but they are superimposable. So thinking about spinning it about this vertical axis, these chloro groups, if we rotate it 180 degrees, will end up on the other side. The oxygens would be on the right side, and that's the mirror image. So they are superimposable. And what about our meridinal isomer? Same idea. We can rotate it 90 degrees. This would be this one. If we rotate it one spot to the right, then they'll be the same thing. Math nerds might try to come for me and say that that's supposed to be 270 degrees because I did it the wrong direction. I don't know. It's not a math class. Questions about figuring out whether those are optical isomers? Cool. So that's all for isomers. We're going to revisit some valence bond theory stuff, which is kind of nice because that's some information that showed up in 1A, bonding theories things. So the bonding in our complex ions, so where we've got a metal center and some coordination groups, some ligands on it, those bonds can be described by valence bond theory. A coordinate covalent bond, like we have between a ligand and a metal center, is the overlap between a completely filled atomic orbital and an empty atomic orbital. So this completely filled atomic orbital would be a lone pair from our ligand, and the empty atomic orbital would be an empty d orbital on the metal. So instead of each contributing one electron in to form a bond, one group is contributing both electrons. And the metal ion orbitals, the d orbitals, are hybridized according to the geometry of the complex ion. S and d orbitals, I guess, SPD. So the hybridizations are the same as we would have seen before. So linear, we've got two orbitals, it's sp hybridization. We're blending an s orbital and a p orbital. Our tetrahedral geometry, we'd be blending an s and all three of the p orbitals to get a total of 4 orbitals, 4 electron groups. For square planar, it's going to be dsp squared, and we'd have an empty p orbital. And for octahedral, d squared sp3 or sp3 d2, where we've got 6 groups. So counting up the number of things we've got here gives us the number of orbitals that we would have. So our valence bond theory can explain the geometry, but it doesn't explain things like color and magnetism. So the complex ions form because of attractions between the electrons on the ligands and the positive charge on the metal ion, which we've talked about. So some Lewis base, Lewis acid things going on there. Our ligand electrons also repel the metal electrons in unhybridized d orbitals. So the metal is going to have electrons in unhybridized d orbitals. In the case of our octahedral ligands, so 6 ligands, this is going to overlap with 2 of our d orbitals, and because of that repulsion, that repulsive force is going to increase the energy of those 2 d orbitals. So that repulsion or overlap increases the energy of 2 d orbitals. whereas the other 3 d orbitals don't have that direct overlap with the octahedral geometry, and so those are going to remain as relatively lower energy. And visually, here's what that looks like. So we've got an energy diagram in our box over here. We've got our energy increasing as we move up along this y-axis, and we've got the d orbitals on the free atom, so with no ligands, and the d orbitals in the octahedral field with 6 ligands. So normally, these d orbitals are called degenerate, meaning that they're the same energy level. If we attach 6 ligands on there, we get some overlap. And taking a look at which ligands have overlap, it's the dz squared, which has what looks like a p orbital in the vertical position, the upright position, and then the donut around it, the torus. And that overlaps with the z-axis groups. We also have the dx squared minus y squared d orbital that's along the y and x axes, where we're saying that our ligands are. So these lobes overlap with where our ligands are. And so that's going to result in repulsion between the electron groups. The electrons are not going to want to be in there because there's already something there. They're repelled away from that area. Versus in our other 3, our d orbitals are off axis. So our xy, they're between the x and y axes. Our yz, they're between the y and z axes. Xz, they're between the x and z axes. So we don't have overlap for these 3, meaning that the repulsion is a lot weaker. And we can quantify the difference between, or at least generally talk about the difference between the energy levels of the ones that aren't repulsed very strongly and the ones that are repulsed very strongly. And that difference is the crystal field splitting energy. It's a description how split the d orbitals are. So how separated those energies are from each other. The magnitude, the size of that splitting depends on both the ligand and the metal ion. So strong field has a large split. Weak field has a small split. So the field part of this we could think of as this energy difference. If it's strong, we've got a big gap between them. If it's weak, we've got a small gap between them. Questions? All right, these effects play into color. So solutions of complex ions often display brilliant colors because of d orbital splitting. So the color that we see is related to the absorption of light energy by the electrons. Reminder of how color works. A black color means that it absorbs all visible light wavelengths. White, on the other hand, transmits or reflects all wavelengths, so nothing in the visible spectrum is being captured, or most of it isn't. And then for any other color, the color seen is the color that is reflected. Or emitted. And so it's the other colors, complementary colors, that are being absorbed. So if you see a red color, red is the color that is coming out of it. It's not the color that's being absorbed. If you see a blue color, the blue color is what's coming out and getting to your eyes. It's not absorbing blue. Emit here also meaning transmit or reflected or whatever. And so there's a color wheel to show us our complementary colors. This is a very basic color wheel. You could get more granular with the wavelengths. So this titanium complex, hexa-aqua titanium 3, is purple. So its color that we see would be in this purple region somewhere, meaning that it absorbs the opposite. That's how the color wheel works. So what you see is one side, and you go to the opposite side, and that's what must be being absorbed. And this is kind of like a broad strokes, very general, very low quality way of doing it, but it gets the job done. If we really cared about getting good high quality results, we would take a look at it with a spectrometer or a spectroscopy device, and then it would tell us, here's all the wavelengths that are absorbed. We did some stuff with this in lab. So we could absorb all the different wavelengths or figure out what's being absorbed. So that's the wavelength absorbed when an electron makes a transition from a lower energy d orbital to a higher energy d orbital. So it's when our field is split, that's the energy for one of the electrons to jump from a lower level to a higher level, is the absorbed energy. And then we see whatever is left over. And we can calculate crystal field splitting if we know the wavelength. So the energy of a photon is equal to Planck's constant times nu, where nu is frequency. Planck's constant is a constant. And frequency is related to wavelength, which is lambda. And then c is the speed of light in a vacuum. And the delta here is our crystal field splitting energy. So our crystal field splitting energy, our CFSE. Just in case you had forgotten what some of those things were. So to try this out, we've got this complex ion, this octahedral complex ion. It's yellow. That's the color that we see. Estimate the crystal field splitting energy in kilojoules per mole for this ion. So the color that we see is yellow. So think about what that means in terms of the light that's being absorbed. If we see yellow, what color is being absorbed? Purple. So somewhere in this purple zone. The purple region here is 430 to 400 nanometers. So let's just split the difference, call it 415 nanometers. So purple is absorbed. approximately 415 nanometers. Just write in some explanation for the notes. All right, and then we've got constants. Planck's constant, 6.626 times 10 to the minus 34. I think it's joules per second. I could be wrong. The number is the more important part, honestly. And then the speed of light, I just call it 3 times 10 to the 8 meters per second. So using the information that's trailing off the previous slide and those H and C values and our wavelength, go ahead and give that a shot. Try calculating the crystal field splitting energy. All right, so our energy that we're calculating is the energy of a photon. We're going to be using this hc over lambda equation. So E photon equals 6.626 times 10 to the negative 34. The important unit that's in there is joules. Everything else will go away. And C, being the speed of light, 3 times 10 to the 8 meters per second. And then on the bottom, our frequency, and this has to be in meters because of speed of light being in meters. So we've got 415 nanometers. Nano is our prefix for 10 to the minus 9. So I just put in 415 times 10 to the minus 9. We could put it in proper scientific notation, and that would also work. It'd be 4.15 times 10 to the minus 7. Or we can just do it this way, and our calculator will give us the same answer. So that's the way that I did it. Because I know my calculator is not going to make an error dealing with 415 times 10 to the minus 9, but I certainly could move in 2 decimal places over. I could do it wrong. I wouldn't put it past me. All right, plug those numbers in. And all right, we'll just keep rolling with it. I feel like I screwed something up, but we'll find out. So 4.78 times 10 to the negative 35 joules. Yeah, I definitely screwed something up. Hold it. Yeah, I put negative 8. I was going to say the order of magnitude seemed way off. So like I was saying, I trust that I can make a mistake. Self-fulfilling prophecy. All right, 4.78 times 10 to the minus 19 joules. It's more reasonable. This is the joules per what? Per one, per photon, per complex ion. So we have to multiply by avocado toast, Avogadro's number. So times 6 point. We're going through it today. So multiply by Avogadro's number. Don't worry, I screwed up putting it in my calculator twice. 288,446.5 ... joules. Now it's per mole. To get it into kilojoules per mole, bump that decimal place over 3 spots. 288 kilojoules per mole. Final answer. Questions?
Why does the 3 times 8 go on top, not the bottom?
The 3 times 10 to the 8
This,
goes on the top because that's where it is on the equation.
yeah,
All right, so for crystal field strength, we've got some generalizations. The ligands, the groups that are bonded, coordinated to our metal center, affect the magnitude, the size of that crystal field splitting energy. We've got the spectrochemical series that lists our ligands in order of their ability to split d orbitals. So going from large delta to small delta. So typically, if we've got cyano groups on our metal atom, our metal center, we're going to have a strong field or a large crystal field splitting energy. Versus if we've got iodide as our group, we're typically going to have weak field splitting. And our cutoff between typically strong field versus typically weak field is between our amine and our aqua groups. The metal ion also has an effect. So if we've got higher charge, that's going to draw our ligands closer. Remember, they're donating electrons. So if we've got a big positive charge, it's going to pull those negative charges in more. And that's going to cause greater repulsion and a larger crystal field splitting energy. This might be a factor if you're looking at different complex ions where it's the same metal and the same ligands, but you're changing the charge on the metal center. That's a possible question that you could see, I could imagine you getting. I don't know if you're expected to know the spectrochemical series for like an ACS exam, for example. I would hope that they'd give it to you. So conceptually, this metal ion part is important. There's some correlation, some relationship, like for our halogens are all weak field, and they're in order of size. So the bigger that it is, the further it is going to be away, the smaller the repulsion is going to be. Maybe one way to think of it. The other ones, I mean, these all have nitrogen in them, so maybe that's a strong field indicator. And this nitrogen is special because it's in a different font, the C in there. I don't know why. They're special. So we'll be coming back to revisit that spectrochemical series. All right, so magnetic properties, because we also mentioned that magnetic properties play a role here. Remember that we've got Hund's rule. Electrons are going to occupy degenerate same energy level orbitals singly, so with parallel spin when possible. When our d orbitals are split, the lower energy orbitals are going to fill first. Once our low energy orbitals are half filled, so let's look at this case, and we've got, say, 2 electrons to add. So if we've got this case, our low energy ones are already half filled. We can either pair an electron in one of the lower energy orbitals, or it can go into the empty orbital of a higher energy. So we can either put it upstairs or downstairs. And the factor that plays, the big factor here, is how far these are apart from each other. So think about if you are in a house that's got 5 people that live in it. You've got 3 downstairs bedrooms, 2 upstairs bedrooms. there's already 3 people sleeping in the downstairs bedrooms. Depending on how tired you are and how far away that upper floor is, maybe it's a 4-story house and there's no bedrooms on the 2nd or 3rd floors, right? You might not want to trek all the way up to the 4th floor. You're like, I'm too tired, I'm just going to crash with one of the people on the 1st floor. So if there's a really big difference here, the electrons are not going to bother going into those upper levels. They'll just go ahead and pair because that's energetically favorable. So if they are not very far split, they'll just go ahead and waltz upstairs and they'll fill in those upper energy levels. If we've got a really large splitting energy though, then it's just favorable for them to go ahead and pair. It's a little bit unfavorable for them to be paired, but it takes a lot more energy to get into this upper energy level. So our example here on the left would be a small delta. Our example on the right would be a large delta. So for magnetic properties, this hexacyano iron 2, ferrate 2, anyway, this thing is known to be diamagnetic. Dia is N2, and the 2 meaning that they're all paired. So everything's all paired up. You could also just memorize that diamagnetic is where all the electrons are paired. And this is because the iron 6 has, the iron 2 plus has 6 electrons. So Fe2 plus has 6 electrons, and the way that they go in because of that large splitting energy is that they all pair up. However, if you pair it with water, water is a weak field ligand. So we've still got 6 electrons. But because it's a small splitting energy, and it's not represented here, they don't pair up. And so they're paramagnetic. You might think of paramagnetic as parallel magnetic. Spin. So instead of being paired, di, 2 directions, we've got some parallel magnetic spin. So we only have one case, one spot where it's paired. The other 4 are unpaired. Generally, our strong field ligands have fewer unpaired electrons. Fewer unpaired electrons, just because we've got those upper level orbitals that are not going to fill up first. Compared to the free metal ion, we would call these low spin complexes. So high split, low spin. And if we've got weak field ligands, then we've got access to those upper levels. There's more room for our electrons to spread out. We're more likely to have unpaired electrons. So if we've got low splitting energy, low crystal field splitting energy, those are going to generally be high spin complexes. We only have low and high spin possibilities if you've got 4 to 7 electrons on your metal ion. D electrons on your metal ion. All right, how many unpaired electrons are there in the complex FeCl6? How many unpaired electrons are there in the complex ion COCN6 4-? Who remembers what our halogen chloride is in terms of strong or weak field splitting?
Is it weak?
It's weak. All of our halogens are weak. So we've got a weak ligand, meaning that our upper d orbitals are accessible. We can put electrons there. And what charge does our iron have in this complex ion?
+6.
It's not +6.
+3.
+3. We've got an overall 3 negative. Each of our chlorides has a 1 negative, so 6 negative plus something equals 3 negative. Our iron must be a 3 positive. So iron here is a 3 plus. Normally, iron has 8 electrons. So Fe would have 8 valence electrons. We've lost 3. So we've got 5 electrons to place for iron. We draw out our d orbital levels, keeping in mind that this is a weak ligand, and so we've got access to those upper d orbitals. We pair our first, or we put our first 3 in unpaired. Since we've got access to the upper energy levels, we can also put unpaired electrons into those upper orbitals. And so we have 5 unpaired electrons.
How do we know that Fe is 8 unpaired again?
Fe is 8 because it's in group 8. When it's just iron. So it would be 4s2 3d6 for its normal electron configuration. We remove those 2 s electrons first when we're removing electrons, and then we remove one of the d electrons as well. So we're left with 5 d electrons left over. All right, who remembers what Cn is? Is it strong or weak?
Strong.
It is strong. It's our strongest, at least for the spectrochemical series we looked at. So this is a strong ligand. So we've got high crystal field splitting energy. Those upper d orbitals not accessible or less accessible. Less favorable, maybe. So we're going to preferentially double up in our lower d orbitals rather than putting them into our upper d orbitals. So we'll find cobalt. Cobalt's in group 9. So normally cobalt has 9 electrons. The cyano groups are 1 negative. Add our cobalt to that and you've got a 4 negative. The difference here is 2, so cobalt is a 2 plus. So we've got cobalt 2 plus. That means that we've removed both of the s orbitals. So we've got 7 electrons to place. Draw out our octahedral complex d orbitals. And we're going to add in 7 electrons. So we add in the first 3, and those are definitely unpaired. And because it's a high crystal field splitting energy, it's unfavorable to put electrons into these upper levels. And so we're going to pair up these bottom 3. And then, with nowhere left to turn, nowhere left to put electrons, we put 1 into our dz squared maybe, or a dx squared minus y squared, one of those higher energy orbitals. So we have 1 unpaired electron. Questions about either of those?
So
Generally, I would refer to a spectrochemical series to know which of the ligands are strong or weak field. So that's this thing here in the middle.
And would they get that, or would we have to memorize that?
Yeah, I don't know. You might be given it. I would hope that you'd be given it. It wouldn't hurt to know that the things that have nitrogen in them, at least on this spectrochemical series, like ethylene diamine, the diamine part, amine, 2 amines, so it's got 2 amine groups, it's got nitrogens in it. These all have nitrogen. I don't know if that's just a coincidence. And then these things are all other stuff. So halogens are weak, water's weak, hydroxide's weak. There's also other shapes. So octahedral, of course, not our only shape. There's also square planar complexes and tetrahedral complexes. For our tetrahedral complex, our splitting is the opposite of octahedral and is typically going to be high spin, since our overlap is going to be less and our crystal field splitting energy is going to be smaller. So we've split differently. Our x squared minus y squared and our z squared are now the low energy ones and everything else is higher energy. Because these tetrahedral ligands are coming in between the axes. So our on-axes d orbitals have less overlap, and our off-axes orbitals have more overlap. That's why it's flipped. And then we've got square planar. You're going to love this. Square planar is more complicated, as you can see. It's this. So our xz and our yz, those would have some up into the sides and down into the sides, various rotations of that. Our z squared is the next in energy, since along the z-axis we've got no overlap, but our torus, our toroid, whatever you want to call it, the donut that's going around is going to have some overlap with each of those. Our xy is in between where our ligands are coming through. And then our x squared minus y squared has perfect overlap with the ligands, and so that's the highest energy. It's a mess, really. It's explainable, but I don't expect you to be able to come up with this on your own. You could come up with it on your own, like I was just talking through. I don't expect it. These are typically going to be low spin. All right, that's all the fun stuff. Now let's get on to the boring real-world applications. So chelating agents, I mentioned earlier, we talked about ethylene diamine tetraacetate, EDTA. It has 6 lone pairs and forms very stable complexes, because when all of our atoms, molecules, whatever, are floating around in a solution, once you get all 6 of those groups on, occasionally 1 or 2 or maybe even 3 might come off at any given moment. The likelihood that you get all 6 of those ligand groups to remove all at the same time and release the metal center is very unlikely. So that's part of why they form very stable complexes, because they're hexadentate. And so you can use things like calcium ethylene diamine tetraacetate to treat heavy metal poisoning. You can add it to your body, and the lead is going to displace the calcium. So this picks out lead and probably some other metals. And then because of how big and bulky it is, that lead doesn't go throughout the rest of your system. That EDTA group holds onto it, and your body can pick it up and remove it from your system. So that's one used for chelating agents. Coordination compounds are also useful for chemical analysis. So some ligands are selective for specific metal ions, and we can use them in chemical analysis, kind of like we did with our qualitative analysis. We can do stuff like that. For example, thiocyanate ion can be used to test for cobalt 2+ or iron 3+. In the case of cobalt 2+, it produces a blue solution. In the case of iron 3+, it produces a deep red solution. So sometimes this can be indicative of having particular ions of different metals in solutions, depending on what sort of precipitates we have, what sort of colored solutions we get. So useful for qualitative analysis. They can also be used for coloring agents. So iron blue is used in ink, paint, cosmetics, and blueprints, and it's a mixture of hexacyano complexes of iron 2 and iron 3. So a lot of like dyes and things, you can make different colors with some of these, depending on how stable they are and what sort of applications you want to put them into. So those are places where these are useful. They also show up in biomolecules. Things like hemoglobin and cytochrome C both contain heme. The heme group is a complex of iron in the center and this porphyrin, which is this flat disc thing. It forms complex ion, picks up iron, and is useful in our bodies. Don't ask me how. It's not a biology class. In hemoglobin, the iron complex is octahedral, so it's got 6 groups, or at least it forms an octahedral complex. The heme nitrogen atoms are in a square planar arrangement, and the nitrogen from a protein for the 5th site, and then either O2 or H2O for the 6th site. So that would be how it carries water or oxygen throughout your body. Or if you're breathing carbon monoxide for some reason, carbon monoxide. And carbonic anhydrase apparently is also a relevant biomolecule, the ACE ending indicating that it's a catalyst. That's not the right word, but it's the right idea, so it's fine. This catalyzes the reaction between water and CO2 in respiration. Again, don't ask me how, but this is how. In this case, zinc is bound in a tetrahedral complex, and the zinc draws electron density, so the water readily loses a proton, and the OH minus reacts with the CO2 to form this carbonic acid anion. Also shows up in chlorophyll, which is porphyrin-based, but this one has magnesium and does not have a surrounding protein. This is essential for photosynthesis. Cisplatin is also an effective cancer drug that functions by attaching to the cancer cell's DNA. And it's got this thing. The chloro groups, the amine groups are on the same side. That's why it's cisplatin, not transplatin. Questions about any of those things that I can say that's a great question too? So this does have relevant applications. It just doesn't apply really to our class, except for that qualitative analysis stuff. Right, we did that. So that'll do it for chapter 26.